Hello, hi everyone. I believe there's some audio issue. That's why I couldn't hear anyone. I hope the room can hear me. Um, and I'm assuming that as a yes. So let me start off. I'm Isha, and today I'm going to present our work, Lumos, which is a domain specific language for frontier model systems certification. This is actually was mentioned by Professor Gagandeep in the morning keynote as well. So let's get started. We start with the premise that frontier model systems are not trustworthy, and this is witnessed by numerous examples shown in multiple works. So, this is one example that we have observed, which shows Gemini producing biased behavior. And in general, developers cannot guarantee whether their tools will produce the trustworthy responses or not, and for that, numerous evaluation methods have been developed. Another example from the recent vision language models is as shown here. When QuenVL is prompted for driving situation, it says that in the most obvious right turn actually, that the right turn should not be taken in the rain. And that could be unsafe for and cause phantom braking, etc. The traditional trustworthy AI pipeline has consisted of evaluating the developed and trained deep neural networks and constantly repairing or retraining them with the evaluation feedback. And prior works have shown that formal certification is a reliable evaluation, and in our work we have attempted to develop that for the large language models and frontier AI systems. The previous evaluation methods for these frontier models has been primarily based on benchmarking and adversarial attacks. And they have a lot of limitations, the key limitations being that they are limited to few test cases. They often have test set leakage as an issue, and there are no guarantees on the generalization of the results. On the other hand, on the related works on DNN certification, this field has traditionally been quite distinct from evaluating frontier models, and it and that has been because these methods are computationally expensive. They're also very customized to certain architectures, and the speed at which these models, like the frontier systems, are developing, the certification methods will find it hard to catch up if they are just traditionally just extended to the new domains. And they're also often restricted to very simple specifications that maybe are the local robustness kind of specifications. And here, the initial ideas we had when we began to form a bridge between the frontier model system evaluation and DNN certification in our pioneering work, LLM Cert. This consisted of the key idea of invoking black box statistical certification to ensure practical trustworthiness over realistic large distributions of inputs and provide high confidence probability bounds. An instance of this framework was also discussed in the first keynote, and these kinds of frameworks work on two key principles. The first one is on quantitative certification. We believe that if a quantitative reliable metric is important, and if it is supplied by statistical guarantee, we can be assured of the reliability of the metric and can be aware of the scope of its generalization. Further, a metric based approach provides actionable insights to the developers, and they can take it as feedback to improve their models. In fact, in our follow up work, we are actually using this kind of feedback to improve the models ourselves. Furthermore, we want a quantitative certifier to be also applicable to closed source models because those are the primary and the state of the art models actually. The second principle we desire out of these frameworks is also related to formal specifications. We want these to be over large input distributions as opposed to individual inputs. Furthermore, we want them to capture natural and adversarial scenarios instead of just very niche cases. And furthermore, we want them to focus on realistic properties like fairness as opposed to robustness or very simple properties. In our prior works involving LLM cert, we developed a family of frameworks concerning specialized properties such as fairness and reading comprehension. So the reading comprehension property was covered in the first keynote. Um, the key shortcomings of these specialized frameworks was that it was very customized to the specifications. When we initially began to develop these frameworks, we were like focusing on very specific properties, and we found it hard to generalize it to any arbitrary specifications. Hence, it is important to somehow find some kind of overlaps between these which were not apparent. Furthermore, with the advancement in multimodal AI, it is important to capture multimodal inputs as well. And most importantly, it is important to capture the validity of the statistical certification always. So we want the statistical certification we do to be valid at all times. For this, we have developed the first probabilistic programming language for frontier model system certification. Our language is called Lumos, and you can access the paper at the QR code. The core idea is around probabilistic specifications, and the objective canonically looks like as shown here. We want to assess the probability that if we draw a random prompt from a distribution, then the model response that is produced by L applied on P is judged as desirable by a response desirability judge. So, with this objective in mind, the certificate we design is based on upper and lower bounds, such that the probability of the objective lying within these bounds is more than some user defined confidence level. So, it can be modulated by the user as per their needs. What we have observed in this particular work is that the key unifying factors behind all these distinct specifications involving arbitrary properties like fairness, reading comprehension, or safety is the fact that graphs abstract the prompt spaces in prior specifications. And I will show examples in this presentation to illustrate that. Our language has probabilistic specifications at its core, and it is developed out of text rich graphs which are used for prompt distribution representations. So it's kind of like an abstraction of representing realistic prompts using graphical structures. And this language has native multimodal support as well. To formulate the prompt distributions, we start off with a text rich graph and form a subgraph distribution on top of it, from which we draw random subgraphs. And to form the prompts, we templatize these subgraphs to natural language by using some programmatic operations. The key constructs of this language, as expected, would be graph elements, prompt elements, and random sampling of expressions. Let me walk you through an example of how we write code in Lumos, and you will observe that this is actually capturing a practical property within a unifying abstraction. So we focus on multi-turn safety certification, which is our latest work, which was published at ICLR 2026 and also deployed within Amazon's Nova evaluation suite. The focus in this work is on assessing the safety of the responses in a sequence of harm eliciting questions which form a conversation. And thus, this is a temporal specification. An example of such a conversation is as shown here, where the user constantly asks harm eliciting queries which could be adapted, but importantly, these should form a conversation and they should have coherent questions all the time. Sorry, is there a question?
Slides don't seem to be changing if you are in fact changing them. It's on slide
I-
14.
I am on 21st.
Okay. I don't know what to
Do you still see slide 14?
like. Would rejoining help? I don't know.
Should I try resharing?
Yeah.
Okay, 1 second. Are you able to
Okay.
see
Yes.
it?
Yeah.
Cool. Yeah, let me know if this issue recurs. All right, so this is an example of a multi-turn conversation. So I believe I was on slide 14, but I was showing you an example of multi-turn safety certification. And essentially, I was discussing what this property is about. So here's an illustrative example for what this property means. We want each query in the conversation to be coherent to the previous conversation that has happened. And basically, the property looks like as shown here, where we assess the probability that if we were to draw a sequence of prompts from a distribution such that these are coherent, the LLM should produce safe responses at all steps. So this is how this is encoded in Lumos, and let me break this down for you in basically abstracting it into a graph abstraction. So we start with a graph of queries. So here I'm showing you a simple toy graph where we have individual nodes represent individual distinct queries which could be harm eliciting, and they are connected with each other by if they are semantically similar and disconnected otherwise. We declare a graph in this language and invoke this by a standard, by just having the nodes and the edges. Then we further invoke a statistical certifier by declaring the certification operation using the key construct estimate prob. So this also informs the interpreter for the language about the different parameters for this statistical certification. And here in this example, following the prior work, we have followed the Klopper-Pearson method of statistical certification, wherein we make like n observations by making trials, random trials from the distribution, and we bound the probability using k observed successes in n trials. We obtain Klopper-Pearson bounds with 1 minus delta confidence, and the key requirement for the prior work was that we should have independent and identically distributed trials. Our language is inherently designed to make sure that such statistical validity is respected. Next, in our subgraph sampling operation, where the subgraphs canonically or abstractly represent the prompts or the prompt sequences as we might have, we start off in this example by sampling any random prompt, which or any random query corresponding to random nodes. So here the programmer has declared by a sampling operation over all nodes. Next, they declare that the next node should be connected to the initially sampled node, that is, it should be the neighbor, and thus should maintain the coherence criteria for a conversation. So let's say node 6 was selected, and in the next step, a distinct but a neighboring node should be selected. And for example, node 7 was selected. We can have this kind of a graph which we combine by like sequential node sampling, and there could be multiple other options that could be generated. To form our prompt, we would format the individual elements of the graph within the prompt template. So in this very simple example, we just directly put the queries from the nodes into the prompt. But in more complicated examples, very diverse kind of templates can be provided, and we have examples of those in our paper. But here we basically see that a conversation is flowing by simple programmatic operations that we have defined on top of the graph. And eventually, we define the observations of the LLM responses using the toEstimate construct, which judges for whether the responses at each step were safe or not, or generally desirable or not. Safety can be judged by numerous kinds of judges. Here, for example, we use the harm bench judge on various different axes of safety. And in general, it could be like any judge model that could be invoked here. The probabilistic certification happens in a loop started off from estimate prob and ended by toEstimate construct. And it could be Klopper-Pearson or any other method. In our results, we see, like here I'm showing results for queries with cybercrime targets. We see very bad performance shown by these models, which are actually large and state of the art. And we see that these models have, so the lower numbers indicate that models are more safe, and higher numbers indicate that models display more attack success rate. So here we see that DeepSeek, for example, has more than 50% chance of being attacked and produce some cybercrime related content. Our language can certify numerous properties, and in our paper, we show examples of all of those. We have temporal specifications, just like what I discussed right now. We have domain knowledge specifications, as in the medical question answering covered in the keynote. And we also have relational specifications concerning with fairness. And oftentimes, like these properties may not be really graph related, but we can always create these encodings that like capture the graph that actually are based on the graph and can still certify. Most importantly, the thing that makes me most excited about this line of work is that creating a language gives us a new way to think about specifications. So earlier, when we started off, we were actually absolutely clueless about how we should even begin defining these specifications. But now having these constructs in our hands, we are able to manipulate them and apply them to very distinct properties and different models to actually create valid and reliable certification bounds. As an instance of this, like to demonstrate what I'm saying, we have created the first safety specifications for VLMs in autonomous driving for scenarios just like as you see here, where where we can simulate weather and other kinds of barrier situations as well. So the way we encode VLM safety is by using scene graphs, which basically correspond to scenes. And these graphical constructs correspond to different entities in a scene and how they relate with each other. We convert these scene graphs to scenes by using standard tools like Scenic, which the PL community has developed. And utilizing these tools, we are able to actually produce certification bounds that show how unreliable these models are. For example, Quen2VL is more than 90% unsafe, which makes me really scared. Here are examples which show the hazard in practice, where we see that, like this is the initial example of Quen VL not suggesting a right turn when it's obvious, and lava simply ignoring the presence of a barrier because it's clear weather. In the next example, this was already kind of mentioned in the keynote, but just continuing and giving more details. Like if we were to integrate, we are able to integrate prompt level verifier Beaver over entire LLM prompt distributions as well. If you just as a reminder for the audience, Beaver gives us sound probabilistic bounds for single prompt outputs. And we are able to combine these bounds for individual prompts over large distributions of prompts to produce certification bounds for these models that how privacy revealing they are. So here we see the aggregated Beaver bounds, which indicate that, for example, Quen3 has like more than 24% chance of revealing the information. So, I mean, privacy, for example, may have lower thresholds because like even like a slight chance of privacy revealing might actually be devastating. So we see multiple examples of how like how the privacy failures are operating, and these models are actually pretty vulnerable is just in a nutshell, that's what I would like to say. So this was again slightly discussed in the keynote, but just to provide more details, we have followed up this work with a failure mode discovery framework, wherein going beyond these specifications, we want to find the ones that are more adversarial for the model and lead to higher failure rates. So essentially, this starts off by searching for failure modes, which correspond to conjunctions of concepts, realistic concepts that could occur. So here are like examples of concepts. For example, a cyclist in the picture and clear weather and a dumpster also in the surrounding. So for searching for failure modes, we essentially conduct a beam search informed by an acquisition function to obtain conjunctions of concepts that lead to high failure rates, and we assess these failure rates by our certification methods. And as examples, we observe failures where, for example, Gemini says that for a very close by cyclist in simulation, Gemini just says slow down, and actually that results in a collision in simulation. In summary, I have presented the first domain specific language for frontier model system certification, which uses graphs as the key abstraction. This language has probabilistic certification at its core, focusing on graphs and actually provides insights that go beyond what was possible by previous evaluations. Furthermore, with the language framework, we are able to think more about specifications and are able to design and connect elements together to create new kinds of evaluations which were not possible previously. Thank you. This is our our work is on the project page as shown on the top right, and also I'm on the job market. So please contact me at my email for any further information. Thank you. Are
Okay,
there any?
thanks, Isha.
Thank
I
you.
think we are over time, so if there are any questions, we can take them offline. Yeah.
Yeah, for sure. Please feel free to just email me with any questions.
Okay. Thank you.
Thanks.